and some examples related to moduli spaces of connections with regular or irregular singularities. So Philip Bolt, who studied the irregular case quite a bit. I want to just give a quick overview of the sort of very general theorems about how you work in this TFT, how this TFT is constructed. And then what I hope to spend the most time on is giving you a sense of how you can do computations with this stuff quite explicitly when you're talking about surfaces. So I want to briefly recall some older work about so-called Alekseev-Grosse-Schomerus algebras and how they appear in this story. And time permitting, I want to just spend the most focus on more recent work. This is with Ian Ley, Gus Schrader, and Sasha Shapiro, which gives a sort of new point of view on cluster quantization as it was sort of created by Fock-Goncharov and studied by many people within the framework of fully extended topological field theory. Right, so the sort of, beyond stating some theorems, the broader goals are to just give you some feel for this 4 category. It's a very interesting 4 category. And sort of show how some really well-established elementary category theory can be used to get a handle on this thing. And aside from just recovering these 2 classical constructions in quantum topology, but by cooking them up in this fully extended way, we give them some new we get some new tools for studying those. So both the AGS algebras and the cluster quantizations, they're defined by generators and relations. So they're sort of defined by fiat. And rather what we're going to do is give an invariant definition and then recover those famous generators and relations. As I'll explain, when we think about the underlying algebraic geometry, what we're really doing is expanding the locus that we're studying to. So in both of these constructions, you're sort of restricting to a place where a group acts freely, and so you're throwing away some stacky points, and we're going to be able to contend with those. And sort of a long-term goal that I won't really talk about, but which motivates me, is to understand. So Tudor de Mafte, Gabella, and Goncharov have some very interesting proposals how to sort of move from 2 manifolds where cluster quantization has been extremely useful into the world of 3 manifold invariants and construct new 3 manifold invariants using this technology. And I think by putting it in this fully extended 4-dimensional framework, it gives us the tools to do that in a rigorous way. Okay, so right, so I want to give you some sense of where this is all taking place. And so we're going to be talking about braided tensor categories. And I want to first remind you of a way to think about these in a more topological sense. So there's a category So there's a category of disks. So these are just 2-dimensional disks. And so the objects are just disjoint unions of copies of R2. And the HOMs, these are, is the topological space of embeddings of disks. Okay, now really I should say whether I'm talking about framed disks or oriented disks, but let me not worry about this level of detail. And so in this category, we have just the basic disk, which is R2, and I'm going to draw that in the plane like here. Can you see when I move my mouse? Is it visible?
Yes.
Yes. Okay.
Mm.
This is a monoidal category, symmetric monoidal category, and it's generated by just a single copy of R2. So that's, I'm going to denote by this disk here, and I'm going to color it with the letter A, which I'll explain in a moment. And so morphisms in this space are given by embeddings. So for instance, here is an embedding of two disks into one. So this is, if the disk was labeled A, this is giving us a map from A, tensor A to A. But I said that we consider the space of embeddings of disks. And so when I say that we consider the space of embeddings of disks, it means that if I would consider an isotopy of embeddings, for instance, here's a map from A tensor A to A, and here's another map from A tensor A to A, where what I've done is I've embedded the disks instead of in the 1-2 order, I've flipped the order. So I have two different embeddings. And now if I choose an isotopy between those two embeddings, well then I have a morphism from this embedding to this embedding given by that isotopy. So that isotopy right there defines a morphism. Okay, so this is the category of disks. It's a very natural thing to think about if you're studying surfaces. And so a fact is that a braided tensor category is the same data, braided tensor categories is the same data as a functor from disks to categories. So that's why I'm labeling it with this object A. So the R2 goes to some category A. And this picture here was telling me that because I can embed two disks, I get a multiplication functor. This diagram here is telling me that it should have an associator, should be a tensor category. And this structure here is the braiding. And the content of the assertion is that that these morphisms and the relations that one usually spells out when one defines a braided tensor category present this category. So it's a presentation of the category of disks in such a way that when you represent it into categories, you get exactly the notion of a braided tensor category. So if you like, that's one way to define braided tensor categories. Okay, so all of that structure is what goes into the objects of this category. They're braided tensor categories. The reason that I wanted to present it that way instead of a more usual recollection of what a braided tensor category is to motivate the higher morphisms in this category. The higher morphisms in this category involve stratified disks. In order to say what the one morphisms are, what we want to consider is the picture here. So we look at R2 again, but we consider R2 with a line passing through it. And when we look at basic open sets here, we have two different types. We have actually three different types. So we have plain ordinary disks that live up here, like A. We have plain ordinary disks that live down here, like B. And then we have those disks that are transversed by R. And so we can form a new category, maybe I'll say disk. So if this was disk 2, maybe this is disk 2-1. And here we have disjoint unions of R2 and this other disk, which is R sitting inside of R2. And once again we consider embeddings of these sorts of things. But now we have this stratification. We have this one-dimensional defect, and our embeddings have to preserve that. So in fact, here we said there are 3 different types of disks. And let me just go ahead and say that what we're going to be interested in is functors from disk 2,1 into cat. And so the first bit of data that we have to spell out is not 1 category, but 3. So we have a category A, category B, and a category C. By those basic disks. So was there a question?
Yeah, could I ask you a quick question? So do you allow disks to be sort of odd-shaped, like banana-shaped, so that they intersect the line in 2 distinct segments?
That's a good question. So I'm going to consider basic disks for the moment. No, yeah. So for the moment, no. The category disk 2,1 is just the union of consists of disjoint unions of R2 and this particular thing. Now, okay. These lie inside a bigger category, which you could easily define, which we will study later, which is the category of stratified surfaces. And if we consider an arbitrary stratified surface, so the question was, what about something like this that has sort of 2 defects running through it? And we will consider exactly examples like this. But this category of disks is sort of the simplest possible thing. And a manifold like this can be covered by these simpler disks. And so we're going to, for now, we just restrict attention there.
Great, thanks.
I'll come back to the more general questions.
Sorry, and I don't, probably I'm missing something basic. So what is the difference between A and B? So I thought that you have, I mean, if you just consider disjoint unions of either copies of R2 or copies of R2 with a line in it, then, I mean, with a disk, either have a line for a disk or you don't have a line for a disk. So what's
yes, thank you, Sasha. You're absolutely right. So, you're absolutely right. So, disk 2,1, if I've written it this way, then you are right. That's just a correction. This is a reasonable category, but I do want to consider colored disks. So I'm actually going to consider disks where I have colors A and B. Thank you. And then the stratification will also have colors. So this sits inside a category of stratified and colored surfaces. And these are the generators in the sense of this coloring. Yeah, that's going to be necessary to allow morphisms between different braided tensor categories.
And I missed the geometric meaning of this color. So like in the formally, what's the difference between A and B?
I'll get to that now. Yeah, thanks for your correction. Now I'll explain how to think about these. So right, so we're considering generally surfaces which have so the general picture that we might kind of imagine that we want to think about is some surface. Maybe there's just a simple disk, but maybe we can imagine it has some genus. And we're going to allow defects. So just codimension 1 defects. And then if we remove those defects, then we just get a disjoint union of open surfaces. And then we're going to color those by some set of colors. And in the present discussion, I'm only allowing 2 colors, but you can certainly consider more general configurations. So I'll choose a color A here and B here, maybe B here, B here, something like that. Okay. And so there's an obvious notion of embedding of such things, and there's an obvious notion of isotopy of embeddings, and so we can make sense. We can ask, what does it mean to have a functor from disk 2,1 to categories? So I'll state it as a fact and a definition rolled into one. I think the first fact about braided tensor categories, you sort of knew what a braided tensor category was, many of us. But this one you can take almost as a definition. So if we look at these kinds of objects, so things like this, these are in one-to-one correspondence with what's called AB central tensor categories. So more precisely, what I'm saying is we fix a braided tensor category A, and we fix a braided tensor category B, and then we look at functors from disk 2-1 to categories which send the color disk A as above here and B as above here, and we ask what is the new data given by C. And the interesting thing is that C has a lot of structure. So
is this related to the Drenfeld center?
Yes, I'll come to that momentarily. Thank you. So first of all, C is a tensor category. Because this C lives on a line, I can play the same game that I played here. I could take 2 copies of C living on a line, and I can embed it into a bigger copy of C, and that defines me an associative multiplication, just like before. But what we don't have anymore is we don't have the isotopy that switches them. So that is not allowed because that isotopy would not respect the stratification. It would warp the stratification. Okay. So a priori C sounds so far like it's just monoidal. But then what this diagram here is telling us is that we have a functor from A tensor B. Remember, those are our braided tensor categories to C. And if you think about this diagram here, it's telling us that this is a tensor functor. So remember that the multiplication of A and B was just given by horizontal stacking of disks. The multiplication of C is given by horizontal stacking of these disks with defects, and those are just compatible. So that's a tensor functor. But what's interesting is that, so let's look at, I want to look at this picture. Let me make myself a new page if I can. I've kind of boxed myself in with this. I need to set continuous scrolling. How do I do that again? Okay. So I want to discuss this picture with a bit more slowly. So suppose that I have, here's C. I can take a little copy of C and I can take a copy of A. And now what this picture gives me is a map from A tensor C to C, because I have the disjoint union of an A disk and a C disk embedding into a C disk, so it gives me that. But now I can factor that in 2 ways. I could first factor it like so. I could take A, map it to C, and then map that C tensor C disk into C. Or I could take A, map it to the right copy of C, and then multiply them that way. So just as Greg was asking about, this is what this, the existence of this isotopy is telling you that you have a map actually from A to the Drenfeld center of C. But in fact, you have the same structure for B. So you get a map from A tensor B with the reverse braiding to the Drenfeld center of C. And this data, that's the Drenfeld center, is what's called an AB central structure. Tensor category. Okay, so those form the one morphisms in our category. And what you should think is that if you had an associative algebra, then the right notion of morphism between two associative algebras, if you're thinking about Morita theory, would be a bimodule. An AB bimodule would give you a good sort of Morita theory between two associative algebras. And this thing, the AB central tensor category, is the stand-in. It's what serves as the bimodule, sort of one level of commutativity higher. And certainly the people, the physicists in the audience, this will be very familiar.
I'm confused about why you have one C and not two C's, because I mean, is C allowed to be colored also or not?
There's only one. I see your question. So far I've picked that there's.
I mean, I'm just talking about just the definition of this disk 2-1. So you said that you have two colors, but this C thing, is it allowed to be colored or not?
C doesn't have a color, but the ambient, but yeah, basically what you're asking, Sasha, is related to this framings and orientations that I didn't sort of want to go into. So there's a framing on C. So when I said that it defines a tensor structure, right? There's an order of multiplication, and there's also a framing up here, and a framing down here. And so there's no coloring of C, but there's a requirement that that C, when it embeds into some other disk, that it respects the coloring and the framing here. So what you might be wondering is, why didn't I draw this picture with A down here and B up here? I think that's maybe part of the question. This is a, so if this disk maps to C, then this disk maps to the opposite multiplication of C. And the opposite multiplication of C carries a braiding structure where A and B are swapped. So the point is that C determines C op. So the orientation that I stated determines the opposite orientation.
Okay. I was just looking at the definition of this disk 2-1. So it has really 3 basic objects, not 4 basic objects.
I can, as I've stated, it has 3 generating objects. It has C, it has R2A, and it has R2B. And as I've stated it, disk 2-1, the fourth disk that we discussed that has A at the bottom and B at the top is not allowed here. And that's just some bookkeeping about the framings. However, if I have a functor from disk 2-1 as I've defined it, of course, disk 2-1 sits in the larger category where I also throw in that other one that you asked about, but that other one is just the dual of C in this monoidal category, so it sort of is completely determined by C.
Okay.
Yeah, that's a great question. Yeah, I wanted to spend some time on this because this is the sort of thing I would usually just sort of sweep under the rug, so I'm happy to go slowly here. This is the mathematical language for handling defects on surfaces and as they arise in this story. So I want to be a bit briefer about the remaining Homs now that we've kind of done that one in detail. So suppose I have 2 of these categories C and D, these tensor categories C and D, and I want to spell out what a morphism is between those. So then what I do is I consider this space here. And then I look at the basic open sets again, and I fix the braided tensor categories A and B here. I fix C and D to be the two input central tensor categories. And then the new bit of data I have to give is a category here. So this is what I'm really spelling out is disk 210, what it looks like to map just 210 to categories. And basically what you get is that M is a bimodule between C and D, but it has an extra symmetry coming from the fact that A can act either through C and then to M, or through D and then to M. So you can encode what that means, and it's the notion of an AB central CD bimodule category. In a moment, I'm going to do a bunch of examples. If this sounds abstract, bear with me. The thing I want to emphasize is that this is a 4 category, and the top 2 levels are algebraic. So these ones were topological. And these ones are algebraic in the sense that because I'm mapping to categories, I have the notion of functors between those categories, and I have a notion of their natural transformations. And so all of the sort of 3 morphisms and 4 morphisms, they're going to be algebraic stuff about category theory, and all the lower degree morphisms are going to be topological stuff about surfaces. So there's a lot going on in this slide. Are there any more questions?
Yeah, it seems a little funny that you have this split between the algebraic and the topological. I mean,
It's just built in. It really is baked in. I'll try to explain. You'll see this split throughout the talk.
I mean, can you go to 5 dimensions in some way? And
there's a 5 category of symmetric tensor categories, which is interesting to study. Basically, you can study EN algebras in any K category, and here we're studying E2 algebras in the 2 category of categories, and so 2 plus 2.
Okay. And does anything special happen for modular tensor categories, if that's what you start out with?
Yeah, I'll mention briefly about modular tensor categories, and I'm happy to discuss that. Essentially, modular tensor categories are the invertible objects in this 4 category. So it's a monoidal category. I can take two braided tensor categories and I can tensor them together, and I can ask, is that equivalent to the trivial category? And modular tensor categories are equivalent. A category is a theorem of ours is that braided tensor category is modular if and only if it's invertible in this.
I see.
Or, sorry, that's not quite if and only if, but
yeah, I know it's coming back. You said that in your Western Hemisphere talk. That's right. Okay.
Yeah, that's right. That's right.
David, can I interrupt with just a comment to Greg's question?
Yes, sure.
And I don't want to distract too much, but so it is possible to kind of define the notion of category itself kind of topologically, because somehow composition in a category is like composition along a string. But David's doing something more sophisticated, because maybe you haven't said it yet, but he really cares about things like exact categories and exact functors, and that starts feeling much more algebraic. And somehow that's, I think, where the algebraicness is coming in.
Yeah, I'm so far I haven't said what kind of categories I want to work with and what kind of functors, but yeah, it is right that that's under the hood. Cool. All right. I want to give some examples. And as usual, we'll start off with some seemingly tautological examples, but they're already the tautological examples are interesting. So if I have a braided tensor category, I can of course think of it as an object of the braided tensor categories. That's by definition. I can also think of it as an AA central algebra. So that's sort of this picture. I can draw sort of a defect here, but which is a false defect. So I can put A here. I can also put A here, and I can put A here. So that's like the regular bimodule. But there's an even more interesting one, which is I can put A, and A. And so I can regard A as a AA central AA bimodule. So this is in HOM 2. So I'll call this A reg. Reg. And well, that sounds kind of tautologous, but there's something that I want to emphasize, which is I could consider what I would get if I would study a picture just like this. I'm going to still put A, and A, but then I'll change A just at the middle here. So I could consider what kind of category can I surround by A's and just a single M. And so that would be a Hom in this category of it's a 2 Hom from A reg to A reg. And so this is very interesting. This is the 2 category of what are called braided module categories. And my pen sometimes dies, but I know how to fix it now. So.
So I have a question. I'm trying to translate this into some kind of physical picture. I know maybe you're going to do that later in the talk. But you know, one thing I like to assign to a disk is the braided tensor category of associated to a VOA.
Mm-hmm.
And then I understand the lines. You know, those are interfaces between rational and conformal field theories. And I understand the disks on the lines. Those are I would call them boundary condition changing operators. But I'm not sure I know what the physics is of your M between the A's and the B's on the line. Is there some physics language that goes with that?
Oh.
Well,
Sorry, Greg. I want you to repeat your question once I get the. Oh, good. Okay, we're almost there. I just need to get this pen working.
You're fixing your pen?
I'm fixing my pen.
Okay.
After this happened last time, I learned how to fix it. So. Yeah, we're almost there. So you're asking about this picture here, right?
I'm just asking. Well, I don't see it.
Here?
You need to share your screen or something.
Oh yeah, sorry. Right.
Yeah, slide 3.
That's right. So here at the top, yeah, this picture here.
Okay, yeah, that'll do.
Yeah.
Well, with the A's in the orbit could be all sorts of things, A, B, C, D. But my question is, what's the physics of the M? Is there any? You see, if I take your the braided tensor category associated with the disk to be the category of, I don't know, highest weight representations of a VOA,
Mm-hmm.
then everything is familiar to me up to the M. That's where I'm losing the physical interpretation. And I just wondered, well, if you've talked to physicists and they had some words to say about it. The answer could be no.
Yeah, I think the relation that I would want to explain there is a role for this in physics, but the 2-dimensionality is kind of misleading in the sense that right, I in this colloquium I mentioned that we're studying sort of Kapustin-Witten TFT on some surface, which is really to say we're looking at, you might imagine that we're looking at a 4-manifold, which is the surface cross R2. And so then this, what looks like just a point in the plane is really a sort of two-dimensional, you know, an R2 defect in R4.
That's very helpful. Now I understand.
Yeah. Okay. Yeah. Thank you. Yeah. The relation to some things like conformal field theory, I think, is to me, it's not at the center of my mind. Not to say that there isn't a good description of what M is in those terms.
Well, it's interesting to remark that if in a rational conformal field theory, if you're starting from the bottom up, everything makes good sense up to the, or at least to me, up to the M.
Right. Right. Okay. So yeah. So this structure that Greg is asking about, it's something I want to spend some time focusing on. But I just want to name that it's in sort of quantum topology, quantum algebra literature. It's been studied a lot under the name braided module categories. So they were introduced by Enriquez and Brochier. They appeared a lot in some computations that I'll explain. And they are important in the theory of quantum symmetric pairs. They go back to some early work on integrable systems of Donin and Mudroff, Majid, and so on. And so it's not exactly answering Greg's question, but the way that they arise is if you have something which is ad-equivariant for the group and you quantize it, then you would expect it to quantize into a braided module category. So things like conjugacy classes, anything to do with monodromies on a surface, when we quantize those spaces, we typically will get a braided module category. Maybe to sort of explain that point a bit more in more detail, I would say a more obvious way that we might imagine encountering a braided module category is from the following picture. I'll draw over here. So here's our plane, but let's imagine that instead of a point, what happens is that a surface sprouts out here. So we have a whole, you know, genus 2 surface or something like that. So any kind of categorical invariant that we assign to this surface, we can sort of think about this as, this gives us an example of a braided module category. So we have A surrounding it. We also have A in the surface as well, but we sort of just put that out of our minds, and we think that the category associated to the surface is a braided module category. That's an important picture to keep in mind. All right. That doesn't look very good. Let me see if that goes away. Guys. Okay, I know what to do here. Okay. So I want to give some examples of simpler structures, which is just examples of these guys. So just the one morphisms. So an important example of one morphisms that I want to consider, if we need to fix braided tensor categories here and here, and I'm going to depict those with the letters G and T to represent the braided tensor category of representations of the group G and of representations of the Cartan group T. And so this is braided with the sort of quantum R matrix, which I, of course, won't write down, but I'll just mention that it has a formula, say for SL2, looking something like this. Some infinite sum here over all roots. And raised in all powers. And this thing is also braided, but with essentially just this simple quadratic term serves as braiding. And a super important observation is that the kind of thing that we can put right here, I would indicate with a B, is the just tensor category of representations of the quantized Borel. I'm saying that the quantum Borel serves as a good one morphism between G and T. And in fact, in examples, it's telling us about parabolic induction and restriction. Okay, so that's a natural statement, but it's really saying something that the Drinfeld center of B is closely related to the quantum group G and the quantum group T. That's a sort of well-known thing. And as I've alluded to, other examples are going to be more related to the topology of surfaces. Okay. I'm really burning through time, and that's okay. I'm going to actually skip this, and just discuss it more colloquially here. So the reason that I care about this 4 category is that we can use it to construct fully extended topological field theories. So I'll just recall that the cobordism hypothesis of Baez, Dolan, and Lurie tells us that we can construct TFTs either of framed manifolds or of oriented manifolds by analyzing the algebra of our 4 category and looking for, in order to produce framed TFTs, we need things called K-dualizable objects. So that roughly says that the objects have duals, the evaluation and co-evaluation have duals, their duals have duals, and so on. And you say that K many times. And then if we want that to be oriented, then there's a group action by the group of framings, and we need to be equivariant for that group action. And if we can find that structure, then we get oriented TFT. And if we can find an invertible object, so that means that an object A, such that when we tensor it with its dual, it doesn't just have a map to the trivial object, but it's actually an equivalence, then those correspond to invertible 4-dimensional TFTs, such as arise when you study modular tensor categories. Okay. So I just want to sort of go through some theorems that get us started in this fully extended TFT. So first of all, the most basic theorem is that this is a well-defined 4 category. I mean, I've been very loose about saying these are the morphisms, these are the 2 morphisms, etc. But it's serious work to, establish the coherence that says that these things compose the way they're supposed to, that the monoidal structure is there. So this is hard work. The basic concepts were developed by Lurie and Ayala and Francis, and the actual theorem constructing this category is split into 2 parts: a purely sort of topological higher categorical part due to Haugseng, and then work of Johnson-Freyd and Scheimbauer. So that should be a dash, which what they managed to do was tie together these 2 topological parts with the 2 categorical parts to cohese those together into something which is a 4 category in a rigorous formalism of 4 categories. So I really want to just take a moment to emphasize that, like, 6 years ago, you couldn't really seriously talk about 4 categories. I mean, it was very hard to construct a non-trivial example of a 4 category before this work that I'm citing here. Besides something that was kind of like the 4 category of 3 categories or some kind of very general thing, and so there's a lot of tools to start actually proving theorems. So the first theorem in this direction is that any braided tensor category at all is 2-dualizable, and that essentially encodes this topological fact that all these pictures that I'm drawing are about surfaces. To say something is 2-dualizable, you need to produce some duals, and it's always just like taking a surface and turning it on its side and coming up with some natural map. So that was sort of proved in 2 different ways. First by Kalak and Scheimbauer in sort of more topological way, and then by Gwilliam and Scheimbauer in a purely algebraic way, which I find quite pleasing. And moreover, not only is it 2-dualizable, but the output, so that produces a two-dimensional TFT whose outputs are certain categories. And there's a formula for computing it, which had already been proposed by Ayala Francis following work of Lurie. Subsequent to those works, I showed with Adrian Brochier and Noah Snyder that you could get one letter up and one dimension up into that pure algebra. So any rigid braided tensor category is 3-dualizable. So now there's a 3-dimensional TFT that you can name from any rigid braided tensor category. And rigid here means that that compact objects have duals, compact projective objects have duals. It's a pretty mild condition. I think the result that Greg was inquiring about is that if I have a modular tensor category, which need not necessarily be semi-simple, then it's not only 4-dualizable, excuse me, it's invertible. In particular, it's 4-dualizable, but the key thing is that it's invertible. Okay. And so this gives us a way to use this sort of machine to define non-semi-simple versions of the Crane-Yetter theory and of the Witten-Reshetikhin-Tarayev theory as fully extended TFTs. And I just want to mention I'll mention to this folklore, if I have a semi-simple ribbon braided tensor category, then it's actually SO3 fixed. Folklore is maybe not fair. This was explained to me quite clearly by Claudia Scheimbauer, Chris Schomer-Priese, and Noah Snyder, but they didn't really ever write it down. I understand that this notion of SO3 actions and maybe more general versions of this theorem are in some forthcoming work of Chris Douglas, Schomer-Priese, and Noah Snyder, maybe in the discussion section. I think I saw Chris here, so he may make some remarks there. So basically the point is we can get invariance of 3 manifolds from this machine. And what I won't go into great detail in this talk is that we should think of those invariants as the outputs of the Kapustin-Witten theory on some 3 manifolds. Okay. Are there any questions about this bit? Okay, and so so following the suggestion of Kapustin-Witten and a sort of reformulation of due to Ben-Zvi and Nadler, the Betti quantum geometric Langlands TFT is the name for this 3-dimensional oriented TFT that you get by fixing rep QG, and here Q is going to be a generic complex number. Okay. So there's a lot of words. Let me say what it spits out for you. If you evaluate this on some closed 3 manifold, you get a vector space. If you evaluate it on a closed surface, you get a category. If you evaluate it on the circle on the closed 1 manifold, you get a monoidal category. And if you evaluate it on a point, you get a braided tensor category, which is rep QG. So there's this nice cascade of structures that it outputs for you. And sort of a basic orienting result is that if you plug in Q equals 1, then Z of the surface is recovering for you the character stack of the surface. So moduli space of G local systems on the surface. And so what that tells us is when Q is not equal to 1, then we have some quantization of this moduli stack that is very important in the Kapustin-Witten theory. Now I've gone very slowly, so what I hope to do is talk about a technique for doing some computations here. I think, but by the way, what time did I actually start? I guess we started a bit late.
No, about
when
8.
When should I wrap up? That's the question, really.
A little past 9, maybe 9:05.
Yeah, okay. We'll shoot for 9:05. Okay.
Mm-hmm.
All right. So So I want to give you some sense for how you do computations here. And let me start with the topology. Because we have a fully extended TFT, we're allowed to do computations on manifolds with corners. So for instance, if I have a surface with boundary, okay, the kind of thing I'm supposed to get from this is, first of all, a category. But better than just a category, it's a module over the boundary. But even better, I can sort of alter this slightly and think of this as a manifold with corners, and I can highlight just a little bit of the boundary. And so what happens is that when I evaluate Z on this thing, what I get is a module category for rep QG, because the morphisms in this category are all bimodules at this level, and if I only have one piece of boundary, then I just get a module for rep QG. So what you should be thinking is, I've sort of categorified, and I'm thinking of rep QG as like a commutative algebra, and the surface is giving me a module over that commutative algebra, and I want to sort of study that. Right, so that's what I'm saying here. This little red bit here, I think of as, I've called it a gate here, and sort of another equivalent way to think of this picture is that I can imagine that I can insert little disks in here. I can just start packing disks in here through this gate that I've opened, and that endows the surface with the symmetry, which is the representation of rep QG. And then the key property that allows all those theorems in the preceding page to be proved is excision, which says that, say I have two surfaces glued together. So here's a genus 2 once punctured surface glued together by across some little disk here, then this I can just write as Z of the one thing, tensor Z of the other thing, over Z of the disk, which is rep QG. Okay. So as long as I can perform these algebraic operations of taking relative tensor products, then I can compute this. I can compute on any surface at all. I can just keep cutting it up more and more like this. So so you can choose your favorite way of decomposing this. For instance, the one that we like to use is called Handel and Combe decomposition. And then finally, so that will get us computing arbitrary punctured surfaces of arbitrary genus. And then for a closed surface, we have to seal up the puncture. And so that tells us that we need to understand these things. But now I want to seal up over the entire boundary. So I have to tensor over Z of a circle. And you note that these are both braided module categories. So just the magic of fully extended TFT translates this whole question into some algebra. Make a decision here. I think for now I'm going to skip what the sort of technical algebraic tools are. Let me just say briefly that if you have a monoidal category A acting on a module category B, so this is tensor, and this is its module category. So this is something that I will say that we don't like, because saying that you have a category attached to a surface, you want to understand that category more explicitly. So there's this machine due to E&O, which builds on a machine of Bar-Beck, which allows you to turn this and express M as equivalent to just the category of modules for an explicit algebra. What the miracle is that when you do computations with this in this 4 category, you can actually perform the computations that you need to do, and you can, these algebras that you need to compute, you can write them quite explicitly. That's a bit telegraphic, but I want to sort of not dwell on this older structure, and I want to sort of state some newer focuses. I want to just start the conversation about stratified surfaces and their relation to Fock-Goncharov structures. So what I want to understand is how can this whole machinery of Fock-Goncharov cluster quantizations fit into a fully extended TFT framework? So first of all, although we talked about defects of general surfaces at the very beginning, I haven't really come back to it. I've only really talked, the only defects I've thought about are surfaces with boundary and regarding the boundary as a defect. So now I want to imagine something kind of cartoonishly like this. Maybe I have a genus 2 surface, and maybe it has some boundary. And now I want to label the bulk of this surface by G. And then I want to start identifying some regions. Maybe here's a region. Here's a region around here. Let me draw the most general sort of thing I might want to consider. Here you've got a region that completely surrounds this boundary. And what I want to do is on the inside, I want to label this by T. And then on the defect here, I want to label it by B. So I want to sort of consider just a stratified manifold, colored stratified manifold looking like this. And I can make perfect sense out of this kind of picture. For instance, I can still chop this up into its basic pieces, and then I can just apply the tensor product formulas as before. Okay, so if Q equals to 1, that is, if I'm not considering quantum groups, but classical groups, I can ask, what is the Ben-Zvi-Francis-Nadler type theorem here? So what is the Ben-Zvi-Francis-Nadler theorem say? And what it tells us is that this is equivalent to what's called the decorated character stack. This is quasi-coherent sheaves on the decorated character variety of this decorated surface. And what this means is that we consider not just G local systems, but we consider a G local system over the G region. We consider the data of a T local system over the T region, and we can consider the sort of correspondence of a it's not quite a B local system, but a correspondence between the G and T local systems that's given by the Borel B. And this is exactly what Fock and Goncharov have studied for many years. And what they've taught us is that classically at Q equals 1, this category contains a bunch of interesting subcategories. And these subcategories are in correspondence with just open subsets, open charts. And these open charts are just equivalent to tori. So just complex tori. And each such torus, they give the name of a cluster chart. And they give us a prescription so these open charts come not canonically from the surface, but we have to choose a triangulation. So given a picture like this, we have to triangulate it in some way. Okay, and each such triangulation determines an open chart, and that open chart is C star to some rank, and that's what they call a cluster chart. And as you change triangulations to a different one, well, you get a different copy of C star to the R, so a different chart. And the change of triangulation corresponds to something that they call a mutation. Okay. So this is a beautiful. There's a lot of beautiful structure, but it's not something that I ever felt I really understood. And what I really didn't understand is when they turn on the parameter Q, then these open charts become quantum tori. So they become, you have some non-commuting variables, x1 through xr, and these guys Q commute. Q to some number times xj, xi. And somehow they're able to understand these charts enough that they can understand the canonical Poisson bracket, and they just declare these charts. They say, our quantization will be this chart, and this will have its own quantization as well by some other variables. And they're able to quantize also the mutation. So there's a Q mutation as well. And so they define a quantum character stack, or they call it the quantum character variety, excuse me. They define a quantum character variety by sort of generators and relations. They say, okay, the quantum character variety is by definition the union of all these rings compatibly with all these quantum mutations. And then they show a lot of, they prove a lot of theorems that tell you that this really is a sensible quantization of the moduli space that you started with. And so the theorem that I'm fortunately have run out of time that I wanted to explain, so this is with Ian Lay, Gus Schrader, and Sasha Shapiro, is that, so for now, let me restrict to SL2. I'll explain what is expected for other groups. So all of this structure, let me put it this way, all of this structure, so these subcategories, the identification with these quantum tori, the mutations that you get between as you change triangulations, all of this comes from this functor Z, from the fully extended. Which is to say, there is a well-defined category once and for all using this abstract machinery called Z of this surface. It's defined once and for all. If I choose a triangulation, then I can go and apply the TFT rules, and it tells me a way to build this surface out of all these simpler triangles. And I just go and I do the computation that the higher structure asks me to compute. And on the nose, I find that I get a quantum torus. And then I say, okay, but that was a choice I made. I'll now make a different choice. I'll choose a different triangulation, and lo and behold, I get a different quantum torus. And then I say, but this was coming from a TFT, so those two choices can't have mattered. So there must be some way to transition between these two choices. And then I go and I say, what is it? What is the mutation that must exist? And it's exactly the one that they write down. So the upshot is that you have a way to understand the Fock-Goncharov construction as not a definition, but as the answer to a question, which is how do you compute this TFT? And so I apologize, I'm already quite a bit over time. I'll stop there.
So I have a question about that. So is this Z coming from a Kapustin-Witten theory, or is it something more general?
It's I guess you would say it's slightly more general. So if you're studying Kapustin-Witten theory and the sort of Ben-Zvi and Nadler picture, then the moduli spaces that you're looking at on surfaces are just character varieties. So the moduli space of G local systems. So here we're adding these, because we're adding these defects, we're sort of changing the moduli problem. It's so for Fock-Goncharov, I think they did it because it's sort of gives you kind of a resolution of singularities of the variety. The issue is that the moduli stack is what this thing computes. So that means that there's some nice space that has a G action. The G action has stabilizers, and that therefore, if you sort of naively take the quotient, whenever you have stabilizers on the stack, they turn into singularities on the variety. And so, at least as they explain it in some texts, that you can think that adding these extra data of the T local system and the B, the correspondence given by B, what it's doing is it's giving you a resolution of those singularities. Or another way to say that is you're gauging the moduli space so that it has fewer stabilizers. And so the precise appearance of these moduli spaces in Kapustin-Witten theory, I'm not sure that I would be the right person to answer that, but I imagine some other people who might like to speak up may say a bit more about it.
Well, but first of all, before we do that, I guess we should thank David for the great talk. Sorry, maybe I could ask a very naive question before we get to the harder one. So you said along the way that the braided tensor categories form this 4 category and it's 3 dualizable. Is that what you said?
Any rigid braided tensor category is 3 dualizable.
Oh, any rigid one. I see. Okay, I see.
But rigid is fairly weak here. It just means that projective objects have duals. So anything coming from representation theory or like a smooth algebraic variety, that kind of thing will be rigid in this sense.
I see. And anything was 2 dualizable, but the rigid ones were 3 dualizable.
Rigid is 3 dualizable. And then to get 4 dualizable, there's various avenues. If it's fusion, then it's 4 dualizable. Or if it's modular, but not necessarily semi-simple, then it's 4 dualizable.
Oh, I see.
Yeah, so somehow 4 dualizability is a very strong restriction because it's telling you like that you have some. If you have a fully extended 4-dimensional TFT, then you could typically write that with some sort of state sum formula on the 4 manifold. Right. That's going to be a summation over all indices of like morphisms and objects in the category, and it forces the category to be quite small in some sense.
I see. But you've carried this out in some examples?
Yes. So the main computations that we have done have been for surfaces and for 3 manifolds. And the reason there is that, you know, the 4 manifold invariants that you would get are, they're not going to have an algebrogeometric flavor, because in order to have something that's fusion, it's akin to being like a finite group. Whereas the kind of examples that we're interested in are more like moduli spaces associated to an algebraic group. So that if you want to study algebraic geometry, you're just not, dimension 4 is not accessible to you.
Right. No, thank you. So I guess we'll open it up to other questions. I actually have to go as well pretty soon, but as usual at this point, I leave the session open and people ask and discuss. to their heart's content. So anybody else can take over with questions and discussions now.
Okay, yeah, please just unmute yourself if you know, I see that somebody has their hand up. Srihar?
Yes, that's me. Thank you.
Okay.
Thanks for the talk. So I'm trying to understand this, well, a quantum character variety as a quantization problem of something. And for that, I would like to understand if it is possible as a deformation quantization, or in particular, a deformation of the Poisson bracket.
Yes, absolutely.
So if you look at the classical character variety of some surface group in a group G, that has this Goldman symplectic form, or Goldman gives a very nice formula for the Poisson bracket between two functions, which are just trace functions. So is this new, so the CHG decorated as it's a symplectic variety, and is the algebra of functions again somehow simply given by trace functions?
Yeah, well, okay, so it's even easier to connect to what you're asking about, even without the decorations, just the without considering the decorated character stack. Earlier in the talk, before we started worrying about these B's and T's, we talked about this thing. And I said, this was what happened at Q equals 1. And I said, when we turn on Q, so if Q is not equal to 1, then I said that we get a quantization of this character stack. And it's precisely quantization of that Poisson bracket that you named. So it's the Poisson, it's the Goldman bracket on the character variety. Mm-hmm. It's also known as the Fock-Rossley bracket on the framed character variety, or it has various names in different contexts, but that's the one that it quantizes. Yeah.
Okay, cool. And I just wanted to understand your, well, actually the definition of this decorated character variety of S. Yep. It's you said it's actually, elements of this set are correspondences between G local systems and T local systems on S.
Yeah, let me just write that. To answer the question, let me just write a bit more slowly what this is a moduli stack of. Is that useful? So the decorated, so a decorated local system on some decorated surface it's a triple E, G, E, T, and F, B. So EG will be a G local system over SG. So that was in the, let me turn on the continuous scrolling here. So we had this, so SG is the region where we've chosen to color with G, ST is the region where we colored with T, and SB is this region with the defects. So we first of all have to give a G local system over SG, mm-hmm. and a T local system over ST. And then this is the choice of a B, so FB is a B subbundle, B sub local system over, of course, SB. And what is it a sublocal system of? Well, at SB, I can take E sub G cross E sub T. So that's a G cross T local system. And I can restrict that to SB. So on the pictures here, I can take the T local system and the G local system. If I'm on the defect, then I've got a G local system just to one side and a T local system just to the other. So I can just take the external product. I get a G cross T local system, and then I look for a B subbundle inside there. So that's a slight rephrasing of what Fock-Goncharov called the decorated local system.
I see, cool.
And so that is the moduli space that's being referenced here.
Right.
Right, and so that also carries a Poisson structure.
Yes, a quick question clarifying something. So you have the G and the H, G and T, they're independent groups. What is the B? That's a group with a map to both G and T, or no relation to G and T?
Aren't all three related? I mean, it's a group. And
Sorry. In all these examples, G is some reductive group. T is its Cartan, and B is the Borel subgroup. And the claim I made back in the example section is that so at the classical level, what's happening is if I look at point mod B, I can think of that. So there's point mod G, and there's point mod T. So sort of classifying stack of G and classifying stack of T. This has a shifted symplectic structure. And this sitting inside here is a Lagrangian. So in this kind of stacky language. But in maybe more down to earth terms, what I can also say is that I don't want to say this. So this picture, when we quantize this picture, what happens is that there was this claim that rep QB is a morphism from rep QG to rep QT in Burr tens, in braided tensor categories. Which is to say that if I take the Drinfeld center of rep QB, so it's a monoidal category, there's a notion of its Drinfeld center. That Drinfeld center receives a functor from rep QG tensor rep QT. And that's a sort of way that you quantize this relationship. So to kind of answer your question briefly, you can't just choose G and T and B to be independent. They have to have this Lagrangian structure.
And it's necessary that ET is defined over a topological disk, and FB is defined over a circle or the boundary of that disk. I mean, that's how these three things come together, basically.
You mean in these pictures here?
Yeah. Yes.
No. So I mean, well, so yes and no. You can make sense of a stratified surface where the T regions, the B regions, and the G. Once you fix G, B, and T, you can just do whatever you like. So you could consider something. In fact, one should consider something more interesting, like, say, I could have a genus 2 surface. I could have G here, and why don't I put a band here, label that with T, and then the interface here with B, and the interface. So I could cuff a genus 2 surface into like that. So no, it's not that the T thing always has to be contractible or contract onto the boundary or anything like that. The invariant, it just has some universal definition. It doesn't care. However, in the Fock-Goncharov story, they always restrict to stratified surfaces that have properties like you said, that the T regions are always just either appearing internally like that, and then this is the boundary. So this one and this one are what they would call punctures. And this is what they would call marked points.
I see. So, but then the question becomes, so again, on the classical character variety, you have the action of the mapping class group by pulling back connections. How would you get that thing? I mean, somehow it has to be some enhanced mapping class group that respects this stratification of the surface, as you said.
Absolutely, that's right. Yeah. So you can talk about the stratified mapping class group. So you exactly. So sort of by construction, if you give me a diffeomorphism of this surface that respects the strata and respects the colors, it will define you an auto-equivalence of this category. And if you compose two of those, they will be coherent up to an isomorphism. So yes, absolutely. This sort of the picture that you're alluding to for the ordinary character varieties, it arises here. And a lot of remember I said that Fock-Goncharov kind of proved a bunch of theorems to show that their construction is reasonable. And one of them is that they, at least some big piece of this stratified mapping class group that we're talking about, they basically, you can represent one of these mapping class group elements that you're asking about as a sequence of flips of triangulations. And they sort of showed that mapping class group, or at least some big piece of it, acts on their algebras. That's the kind of thing that you don't have to show when you define it this way. That thing just acts.
But then there has to be some compatibility condition of the triangulation with the stratification. It cannot be just any triangulation.
No, that's a good question. The category doesn't have a triangulation. And when you define the category, you don't fix a triangulation. It exists canonically, and that's the thing that is true here, which was not true in Fock-Goncharov's work. There's just a category that's well defined and is interesting to study. Once you choose a triangulation, it gives you a decomposition of that category, and then that decomposition, moreover, determines you a distinguished open subcategory. So you are correct that those subcategories won't be preserved, at least a priori, by an arbitrary mapping class group element, unless that mapping class group element respects the triangulation.
Right.
And so you're absolutely right. So if you want to actually get an automorphism of a given chart from a mapping class group element, which is something that they care a lot about, then your mapping class group element has to preserve the triangulation. So one way to do that is by doing a sequence of flips that change the triangulation, and then you come back to yourself, and that's the kind of thing they study. But the whole category itself, it's defined without reference to a triangulation. It's preserved. It's just that the subcategories get jumbled around.
Right. Yeah. And right. I mean, and it doesn't depend on the chosen triangulation. The decomposition does, I guess, as you said.
Right.
But
you can. Right. This category exists once and for all, and then one can study it by choosing a decomposition. It's just like state sum models, like in Toraya-Viro, there's some well-defined three-manifold invariant, and if you wish, you can decompose it into tetrahedra and do some big computation that appears to depend on that. It's like that.
Right, and okay. It's so another one thing about these quantum groups is that if you fix Q to be a root of unity, something special happens. In particular, you start getting finite dimensional representations. This, and also, I guess, for the Witten-Reshetikhin to arrive, in that case, the level is actually the root of unity as well. Is something special happening for these character varieties if Q is a root of unity?
Yes, absolutely. Yeah, and it happens in the nicest possible way that it happens at the fully extended level. So let me maybe say it like this. If Q is a root of unity, say Q to the L equals 1, then there's a very famous functor constructed by Lustig called the quantum Frobenius. Which takes the classical category of representations of the group G and embeds it in the quantum category.
Oh, wow. Okay. And it's an embedding in particular.
Yes, it's an embedding, definitely. And moreover, it embeds it not just in the center, but in the so-called Muger center. So elements of rep G braid trivially with other elements. So what that means is that okay, this defines a fully extended 3D TFT, and this defines a fully extended 3D TFT. And so that's a really nice thing because it tells you that the invariant, the quantum invariant of any surface or three manifold has maps to and from the classical invariant, so the actual character variety.
Right.
So indeed, you can, and moreover, the other fact that you're alluding to is that so this category is not modular, but it's sort of modular with respect to this category. So this category is not invertible, but it's invertible with respect to this one. So somehow this map going this way is some sort of Morita invertible map. And so what that says is that the quantum category at a root of unity is like an invertible sheaf of categories over the classical variety. So it now is really telling you something about some classical cohomology of the character variety.
Yeah.
So this story is written about in a paper of mine with Safronov, with Ganov, myself and Pavel Safronov. It's called like quantum Frobenius something. But again, the nice thing is that you don't have to construct this. It just falls out from the formalism, and then you can try and compute it.
Very cool. Is the geometry of these quantum character varieties? So now it's going to be a little. If you look at the character variety of a compact group, let's say into SUN, then the character variety is singular, but it's compact.
Mm-hmm.
And in particular, if you, trying to come to this geometric quantization thing. So, and in particular, if you choose a complex structure on your surface, the character variety becomes a Kähler manifold, and there's a line bundle, the non-abelian theta line bundle, and you can look at the space of its sections, and that turns out to be a Hilbert space, which depends on the complex structure. So at the very least, if one chooses a complex structure on the surface S, does that give a different Kähler structure, let's say, on this stack, on this decorated stack?
Yeah, that's another nice question. Right.
Simpler.
So
we can try to figure this out. So what is the tangent space to this stack at a generic point?
Yeah, it's going to be a complex version of the story that you're familiar with. So it's like omega. It's like omega 1 of the surface with coefficients in the adjoint bundle of E is the Kähler space.
Right, that's the classical story.
Right, and that's the for the compact group, but the exact same story is true for the complex group as well. So so instead of it using the complex structure to get a Kähler manifolds. Here because everything is holomorphic, symplectic, you get a hybrid Kähler manifold. And the catch is that, okay, the subtleties are in the details. There's an open, I keep saying the word stack. There's an open substack of this character variety, which is actually where the G action is well behaved, and it's actually a manifold.
Mm-hmm.
And that manifold is hyperkähler. There's a CP1 family of complex structures on it,
Mm-hmm.
and one of those complex structures is the Hitchin moduli space that you're asking about.
Yeah, no, but that's for the undecorated story.
Oh yeah, sorry, yes, exactly. That's all for the undecorated story. For the decorated story,
So you set up the question very nicely for yourself here.
yeah. So for the decorated story,
I mean, it would be very nice actually to describe Higgs bundles coming from this GTB construction somehow.
yeah, I mean, the line of questions you're asking now are good, but they're already interesting as completely classically, and I think they're somewhat understood. At least they're remarked upon in papers of Goncharov. Essentially, the decorated character stack is some partial resolution of singularities of the character variety. Sorry, let me try that again. The decorated character variety that they construct is a partial resolution of the singularities of the Hitchin moduli space. And it's maybe not so clear, but when you introduce these B's and these T's, you're not changing the dimension of the space, and you're freeing up some of the stabilizers. So at those places, you have resolved the singularities. However, there are still it's not that it's a smooth variety. It still has singularities, and in Fock-Goncharov only restrict to this open piece.
Okay, so to the smooth part only.
Yeah, they're only considering their work because they have these charts. I mean, every point in their variety by definition, like their classical variety is they just say more or less by fiat, let's consider the union of all these C star to the R charts. Well, that's obviously smooth, right?
Mm-hmm.
But their construction sits inside a singular variety, and that is the quotient by some stack, and somehow what we're constructing is the stack. From that, you can take the quotient, but I don't know. Yeah, I don't know that I'll be able to say anything that's very exciting about like the real geometry of what's been resolved and what fibers look like, the kind of things that you would usually care about in that domain. At least at the moment, I don't have anything to say about it.
Okay. Just in regards to that, I have a different. I'll just mention it. So, yeah, is the locus of singularities? Does it have codimension bigger than 2, by any chance?
That is another very good question. As far as I know, that is a modification of the statement you said is a conjecture.
Okay. What is the modification?
Yeah, so a modification of that is a strengthening of what you said would imply is a conjecture. So at least for some large class of stratified surfaces that Fock and Goncharov consider, they conjecture, okay, so you have the actual decorated character variety, which is not the union of these charts, but is just, you just take the quotient by G and you get what you get, and it's singular, as you said. What they're doing is defining the union of all these charts, and by construction, the union of all these charts is an affine variety, and the algebra of functions is just a ring generated by a bunch of, it's inside some big rational functions, ring of rational functions in the different variables. They just take the union of all these rings, and so they get another affine variety. And that's what they would call the upper cluster algebra. So those are functions which are regular in every chart. They conjecture and maybe prove in some examples, it's certainly a very open question. They conjecture that even though they've chosen this subvariety with these charts, they conjecture that the algebra of functions they construct is the actual algebra of functions of the singular thing that you started with. And of course, that's essentially equivalent to saying that the difference is in codimension 2. And since this is smooth, that difference contains the singularities, and therefore the singularities are in codimension 2.
Right. So Nigel Hitchen used this trick, the Hartog's theorem, in his original.
Yeah, exactly.
So I would have to go soon, but I wanted to ask you a question which is slightly different. And may I? Is that all?
Of course, yeah.
It was trying to understand, well, not even the quantum Betti Langlands, but just the classical, if it exists, Betti version of geometric Langlands.
Of the duality, you mean?
Right.
Yeah. Yes.
So in the Betti version, I mean, so the question is, for the class, well, for this Balens and Drinfeld story, you have Hecke operators acting on the stack of, well, on Ben-Zvi. Ben-Zvi cross the surface, but you can fix a point and play the game that way. In the Betti version of geometric Langlands, do you expect to have any correspondences or an analog of geometric Hecke operators acting on the character variety or module of local systems? So the reason is I have I can construct correspondences on the character variety for any normal subgroup of your surface group. But I was doing this because I wanted to study the character variety in the case your curve is a modular curve. So the fundamental group is a congruent subgroup of type x0 n. And in that case, you have natural Hecke operators, and one can get an action of Hecke operators as correspondences on the character variety. And I was wondering if this might be useful in geometric Langlands on the Betti side.
Yeah, right. I see. So you want to sort of emulate this ranking gate scoring stuff about like if you could. So if you're saying you understand this Hecke operators on the sort of Ben-Zvi side, and you want to know if that kind of analogous action exists on the character variety side, and then try and make the geometric language equivalence equivariant for that, something like that. Is that what you mean?
David, you went 3 steps ahead. I would just like to get some correspondences on the character variety. And yes, of course, they would only be, of course, if they're natural, then they better be equivariant with respect to this Langlands map.
Well, so I could maybe guess where something like that might arise, but more immediately to the point, I don't actually remember if I can't remember in the Ben-Zvi Nadler initial paper if they made a proposal about Hecke operators. So I can't remember, but yeah. There's something I sort of want to explain about the Hecke category.
By the way, the approach that Witten and Kapustin take on geometric Hecke operators, that should translate to, I mean, because they can define their, Well, I guess Beilinson and Drinfeld do the same thing, but because you can define it as a homology class in the product of your Higgs moduli spaces,
Yeah.
you can apply the non-abelian map to simply, replace everything by local systems instead of Higgs bundles. So the existence, I guess, maybe it's clear from there. I'm not sure.
Yeah, the only thing that I'm worried about is if you, the categories that appear in the Betti geometric Langlands or in this talk are, so there's the Hitchin moduli space, but and they're related by this hyperkähler rotation, but the categories that are appearing, this category of quasi-coherent sheaves, is not respected by the basically by the Riemann-Hilbert correspondence, right? So you have, so that picture that you said,
shouldn't at the category level the relationship, I guess, should be coming from the geometric Langlands program? The quasi-coherent on this side are derived bounded category on the stack side.
But the thing is that okay, so you have, so
the problem that I see is the Beilinson Drinfeld picture is for the stack of, so it's on bun G, and when geometric Hecke operators act, they in particular change the degree of the bundle. But on the local system side, you're only on degree 0.
Yeah, I think that's related to what I sort of wanted to say.
Okay.
But yeah, exactly. I mean, I would be very inclined to believe that there's an analogous story on the Betti side, but I'm not sure that one could just formally lift through sort of Riemann-Hilbert.
No, I agree. One cannot just simply use this non-abelian Hodge correspondence to say, okay, these are the geometric Hecke. I mean, it has to be much more complicated. Well, I think it's right. If they exist, they have to be more complicated and not simply given this way.
Yeah, I want to just draw one picture. So one thing that I think often happens in this Betti story is that things that were analytic before become topological and sort of category theoretic. So just one example that you wouldn't consider in Fock-Goncharov, but I would like us to consider is to take the two-sphere. Make sure I'm saying this right. Yeah, the two-sphere, and again with G in the bulk and T here. So this is, so Z of this is, can be identified with a category that I'll write suggestively as DQG mod B modules. And this category is deformation in a precise sense of the Hecke category. So of some B cross B equivariant D modules on the group G. So, right, if I were looking for sort of trying to look at decorated character varieties and produce these Hecke modifications on the Betti side, I would start with this picture and try and do some topology, but it's not something that this realization is only it's something that Ben-Zvi told me a long time ago I should be able to do, but only recently could I actually see why. So the applications to something like Hecke operators, I'm just not up to speed on. But that would be where I would look for it on the.
I'm just copying the diagram and then I have to understand it because. So what is going on here? So Z of surface with this thing should be some category. That was your.
That's right.
That's what happened, and you're claiming that the category is the category derived by. I mean, See,
No, that's not derived. Sorry, this is something easier. This is DQ modules. So the Hecke category, or one way to study the Hecke category is to look at D modules on the coset space G mod B mod B.
Right.
And I'm saying that category has a natural Q deformation. Which I'm sort of abusing notation and just writing as DQ modules on G mod B mod B.
Great. Okay.
It's So
they're D modules on this stack, basically G mod B, or they can be thought of as functions on the cotangent bundle of this thing. Well, I mean, I understand it's much more elaborate than that, but
it's a quantization of functions on the cotangent space, and then the Q is saying that instead of having a sort of differential, when you talk about D modules, you have vector fields. Here you have like a finite step symmetry. So Q is an actual.
So wait, so the most important question over here is that G is being considered over what field? Is it, I mean, G with values, so is it over the field of functions of S2 somehow?
No, it's just G, just the complex numbers.
Okay. Okay.
But this is, there's this whole story, like this is some kind of categorification. This literally is a categorification. If I take HH0 of this, I get the Hecke algebra. I get the, let me be careful. I get the Hecke algebra. So I have to be careful about gradings, and there's some twisted D modules, but so that I get the Hecke algebra from this thing, and somehow, so this, in more classical approaches, you would consider G over like FP bar mod B, and then you would take some Frobenius action, et cetera. So this is like the complex group analog of the classical construction of the Hecke algebra.
I see. I mean, generally, the stack of bundles on a curve is this double coset space, but then stack of G bundles, and but then you look at G with the function field of the curve.
Yeah, right. I guess there would probably be another one.
You're right. I mean, given that the curve is defined over a finite field, so it comes down to the same thing that you've written on the left with this GFT bar.
Yeah, I mean, there's not. There's again going to be some sort of Riemann-Hilbert correspondence which would then reference the loop group like you're talking about. If I didn't think about this as S2 with this topological defects, but I thought about CP1 and the moduli space of if I thought about something like Bun-G CP1 where I have to do something at 0 and infinity. I can't remember now. I'm getting a bit sleepy. That would be what you would expect to see on the other side of Riemann-Hilbert. And then somehow you would be wanting to study the attaching data of a G bundle. You have CP1. You would be looking at Bun-G of C star. And the bundle at 0 and infinity is going to be some somehow that data is going to involve the loop group like GFT, something like that. sorry, I'm right. Right. Sorry, that's probably where you were wanting to see like me write G of t.
Absolutely. So you threw in the function field of CP1. I think right.
Yeah. So, but on the Betti side, you just have this much sillier looking picture where you just have, there's nothing as sophisticated as a loop group. It's just the finite type group G, like just, GLN or something. And the Borel that was being this, like G, what was G of t in the Johari story. Here is just the Cartan with this correspondence.
So do you have an idea how to see some kind of geometric Hecke correspondences on the right hand side? Am I wrong? I mean, I think I'm wrong. I'm not sure. Doesn't this coset space have some natural correspondences?
This one does. This one does, coming from some geometry. When you have this Q here, it's going to, you kind of lose the geometry because this is just defined as some formal deformation quantization of this guy. And it's not actually D modules on some space. So the correspondences here just come from something naive like, if I take G mod B cross G mod B, I have a map to G mod B. There's some push-pull stuff. I'm not going to write it down. And that's where these correspondences come from. Here, when you turn on the Q, you can't just say that D is a functor and these are some maps of spaces because this DQ doesn't work like that. But what I would guess is that you could topologically, what you tend to do is you replace all that geometry with some simple topology. My guess is that it would involve some three manifold pictures. So if you have some surface, with some of these defects, maybe like a defect here, you're gonna grow it out into some three manifolds, and then maybe put that, attach this guy. So something. Yeah, I'm sorry, I'm getting really
tired.
Something along these lines involving three manifolds kind of has to appear.
Sooner or later, I understand.
Yeah, because another way to say it is that what you really want is that there's the B theory, there's the G theory, and there's the T theory. And B was supposed to be a morphism between G and T. B is a morphism and Burr tense between G and T. I can talk about rep Q. I could integrate G on some surface, or I could integrate T on some surface, and then I can draw this kind of picture where I take a three manifold. I've got my surface. This one up here is all T's, and this one down here is all G's. I can try to put the exact same surface halfway between, color this by B, and then construct the three manifold, which is like that. So I have a G local, so now it's like before, but in 3 dimensions. So I have a G local system down here, T local system here, and at the interface surface, now I have a B reduction. That literally is problematic to define, the functor that would correspond to this picture. But I would guess that you could, I would guess that some picture like this, but where this simple two sphere enters in, you could actually define that three manifold.
Is there a similar picture? Well, first of all, if you put more T's instead of just 2 on S2, Is the right-hand side still simple to define?
That's a good question.
I mean, simply topologically speaking, you're going from the fundamental group being Z to free group on more than one generator.
Yeah, right. I think it's not so bad to contemplate, but I don't think it will. But the point is, I won't have a monoidal structure anymore. I don't think. At least I can't see what the monoidal structure would be.
Actually,
yeah, I'm not sure. There's certainly there's of course no instruction to define the category, and if you had only 3 or 4 punctures, then you could say pretty explicitly what it is.
So three is very good. I mean, because if you have 3 punctures, this thing becomes a pair of pants.
Yeah, exactly.
And you can glue these pair of pants together along the red circles or the B's. I mean, this will bring back to the original pictures that you were.
Yeah, exactly. That's right. Yeah.
So then
I mean, in fact, that's more or less why this thing has a. I mean, that picture will be related to why it's monoidal, I think. But right, yeah.
I see.
You're asking great questions, but I'm kind of not.
So let's do this. I think I have to leave. Yeah, it's 5 as well. Maybe we can talk later or.
Yeah, that'd be great. Yeah, I don't think we've met before, but your questions are really.
So I'm Shehryar Sikandar, and I am a postdoc at Rutgers working with Greg.
Oh, okay. All right. Oh, fantastic. Okay.
Yeah, and we're studying. Well, we're studying. He would say class S theory, where the UV curve is a modular curve.
Okay.
Mathematically speaking, Hitchin system on a modular curve.
Okay.
And
okay.
Trying to get the Hecke operators to act on these spaces. So the arithmetic Hecke operators that come from the modular curve structure.
Okay.
So, I will shoot you an email. So, I mean, I can find you online, I'm pretty sure, on Google. So,
yeah, definitely shoot me an email. And let's find some time to talk.
Yeah, that'd be great. Okay, I have, well, one more question. Maybe if you just have a very quick answer. Is it possible to define these quantum character varieties as Helm spaces? Because the classical one is a Helm from, well, it's isomorphism classes of homomorphism from pi1 to the group.